Welcome to lesson 26. So we're going to actually go through an example now. We're going to calculate a test statistic and talk about writing up that conclusion. And we're going to go from the very first step, asking our question of interest, through that two-part write-up for a hypothesis test at the end. So when we make our decision, we make it typically based on the value of our p-value compared to a significance level. So in general, our p-value, it's going to tell us how strong our evidence is against the null / for the alternative. So we usually like to say that our p-value provides support for the alternative. The smaller the p-value, the stronger the evidence. So here, before you calculate a test statistic and a p-value, you need to specify your significance level. It's really, really important. This is saying, okay, well, if my p-value is below this point, I'm going to reject the null and go with the alternative. And we use the Greek letter alpha. It looks kind of like a fish. And typically, we're going to use either 0.10, 0.05, or 0.01. You'll notice with confidence intervals, we usually have 90%, 95%, or 99%. If you added together, you would get 1. Like 0.10 plus 90%, that adds to 1. 0.05 plus 95% adds to 1. So making decisions here. Our p-values, they give evidence against the null / for the alternative, right? Because if you have enough evidence against the null, that's really support for the alternative. And the smaller the p-value is, the less likely that your null hypothesis is true, given what you saw in your sample. So if the null hypothesis is true and what you saw in your sample is really, really extremely rare, maybe we don't believe that the null is true still. Large p-values, you want to be careful. So they don't provide strong evidence against the null. They provide weak evidence. They fail to give convincing evidence. They don't give support. They never give support to the null. You never support the null. That's never how it works in stats. So here, if your p-value ends up being less than or equal to your significance level, you're going to reject the null and conclude, okay, we believe that the alternative is true. If you have a big p-value and it's bigger than your significance level, we fail to reject. So it's weird language, but we're going to say we fail to reject. Do not say accept. Fail to reject is very specifically the phrase we will look for. And it will say, okay, I don't have enough evidence to conclude the null is true, or the alternative is true. So small p-values between 0 and alpha, you reject. Big p-values between alpha and 1, fail to reject. You can almost think of it as you're a prosecutor and you either have enough evidence to get a conviction or you don't have enough evidence. But you don't prove the defendant is innocent. That's not your job. You're the prosecutor. So here, we also like to talk about the strength of evidence. How strong is the evidence? So in general, if we have a p-value between 0 and 0.01, we call it very strong. You might even call it convincing. So very strong evidence. If it's between 0.01 and 0.05, it's still pretty strong. If it's around 0.05, so honestly probably between 0.04 and 0.06 roughly, I'd call it moderately strong. You would say, okay, there's some evidence between 0.05 and 0.10. Anything 0.10 and bigger, we're going to say little to no or very weak. I don't like to say no because it implies that there's zero evidence. That's not quite true. Little to no evidence. So smaller p-values are stronger evidence against the null. Larger p-values, they provide little to no or inconclusive evidence. So in general, you have to get a more extreme test statistic. The tinier your significance level gets. And you never want to say accept the null. Never, never, never. We never say the null is true. We either say, hey, we believe the alternative is true, or we don't have evidence that the alternative is true. We have very, very peculiar language like that, and a lot of times it leads us to talking in weird double negatives, and I will try and avoid that. Also, p-values, they're between 0 and 1. It's really rare to see them exactly equal to 0 or 1. It can happen, but no, your p-value cannot go higher than 1. So if you have a p-value, especially like two-sided p-values, they should never be higher than 1. So this is a template that I really strongly recommend making sure you have this information somewhere. So this is our two-part conclusion. So two-part conclusion. This is our template. So this is our first part, where we say we either reject or fail to reject the null hypothesis with a p-value of, and then you can put the number here. Later, if we're using a t-table and it's a range, you could say a p-value between this number and this number. And then at the blank significance level. So you pretty much just fill those in. This part's not going to be very variable too much. Then this second part, this blank's a little deceptive. It's usually longer. So using that spectrum from a couple of slides ago, very strong evidence, little to no evidence, to conclude that the alternative hypothesis is, in words, is true. So the mean train trip time for all trips between Florence and Rome is longer than 94 minutes. That kind of idea. So definitely strongly recommend practice writing out the alternative hypothesis in words, because it goes out here. So z-test for a mean. So for week 7, we're going to live in the world where we know what sigma is from the population. So we want to test the average value from just one population. So we're not comparing groups. That's what that means. So our conditions, do we have a random or representative sample from that population? And then do we know that our sample size is big enough that the central limit theorem is going to kick in? Because if it kicks in, then we know the sampling distribution of x bar is going to be roughly normal. And then we want to make sure that we know sigma. And once we do, there are 3 possible, so notice the null hypothesis is the same on all 3 of these. The alternative is what changes. So maybe if you want to just say, hey, is the mean lower than some amount versus is it higher, or is it just different than? So your p-value, if it's lower, is just going to be the lower tail. So you're going to want to find the probability lower. If it's upper, you're going to go above. If it's two-sided, you're going to find your one-sided p-value and multiply by 2. And we can go through that. So your test statistic, it's going to be x bar, so what you saw in your sample. So whatever you observed in the sample, minus, this is mu naught or mu 0. This is the claimed value, over sigma from the population over the square root of the sample size. Which for the train example is really, really nice because it's 25. So we're going to discuss this particular test this week because it's probably one of the simpler tests. But no, in reality, we usually aren't fortunate enough to know the population standard deviation. Usually if you know the population standard deviation, you also know the population mean. Which most of the time you don't know, because why would you test if you knew exactly what it was? Okay, so now we're going to return to the train trip time, so between Florence and Rome, and we're going to go through all of the steps and complete this hypothesis test. So here, remember, we have a commuter that goes between Florence and Rome, and they say, hey, you know what? They claim that the average trip time is 94 minutes. I think it's longer. So they go ahead, they collect a sample. Our question of interest. So remember, for a hypothesis test, this should be in the form of like a yes-no question. So my question of interest is the mean or average. It's okay to put average as well. Trip time. So that right there is my variable of interest. For all train trips between Florence and Rome, probably with this particular company, but I don't know how many companies are using that railroad. And then here's the part that really gets at the alternative, longer than 94 minutes. So is the mean trip time for all train trips between Florence and Rome longer than 94 minutes? So just note, we're going to look for all of those things. Is it a yes-no question? Does it have mean or average in it? Mean or average what? And then what is the population? And then the actual like longer than 94 minutes. What's really cool though, is if you have this set up just so, right here, you have your parameter of interest all ready for step 2. So step 2, we're going to say what is our parameter of interest. So I want to know the mean of all the trip times. Oops. So notation wise, mu is my mean trip time. And then if we ask for like words context, we mean this. So mu is equal to the mean trip time for all train trips between Florence and Rome, at least with this particular company. So inventory, I want to find out, okay, what information did they give me? So like, for example, they took a sample of size 25. They have a sample mean, so this is the mean from the sample. Oops, 99 minutes. This is a big one that's easy to forget. What is the claimed value? So what did they claim? That's that 94 minutes. So then now we're talking about the standard deviation. So the train website states train times vary on average about 10 minutes. That vary on average means standard deviation. So 10 minutes is my standard deviation for the population. So if I want, then I could calculate sigma of x bar. So the standard deviation for the sampling distribution of x bar. So that's sigma of x over square root of n. It's going to be friendly this time. So it's going to be 10 over the square root of 25, which is a perfect square. It's going to be 10 over 5. It's going to be 2 minutes. So that's handy. So then state my significance level. You might notice, if you read this entire thing, there is no significance level stated. Most of the time we will state one, but any time we don't, you can assume that alpha is equal to 0.05, that we'll use a significance level. So this is a default. So if we don't specify one, use 0.05. And then my hypotheses. So we filled this in earlier. So this is my mean trip time. The null hypothesis should always have an equal sign. And then what goes here is what's claimed. So 94, and then the units are minutes. So this is just default status quo. This is what the company's claiming. For the alternative, I want all of the same things, except the sign has to change. So what goes here is, we think that the frequent writer says they're convinced the time is longer, so it's higher than 94 minutes. So this is a one-sided test. So this means when we calculate our one-sided p-value, we're done. That's the p-value we want. We don't have to multiply by 2. Checking our conditions here. So we want to know, do we have a random sample? with no at least major issues of bias that we can see. So they went ahead, they took a time of, they took 25 random rides. Hopefully they didn't ride 25 random rides, they just captured how long they were. So I'm going to say yes. The 25 random rides were selected. And then, do we know that it has a normal distribution? We have 25. It depends. As long as the population isn't very skewed or has outliers, it's probably okay. But it's worth noting that if we do have very skewed data, this will matter. It won't kick in. The easiest way would be to actually go ahead and make a histogram of the 25 train times. And if that's roughly symmetric or roughly normally shaped, 25 will definitely be enough. But if it's not, you're going to need more than 25. And then our third step, the population standard deviation is known. So we're lucky enough to know it here. Sigma is equal to 10 minutes. So check. So for sure, we meet the first and third condition. That second condition, it depends. We would probably need to have a histogram of the data set itself. So now that we went ahead, we've gone through those steps, we can actually calculate the test statistic and then our p-value. So 10 minutes. I'm just filling this in again, so 2 minutes. And then 94 minutes. Okay. So my z test statistic is going to be what I saw in the sample minus what's claimed over sigma of x bar. So it's going to be the 99 is what we saw. It's higher than the average, right? So we should get a positive z test statistic. Minus the 94 is what's claimed over 2. And I'm going to get something like 5 over 2. It's equal to 2.5. So one thing to look at, if the null is true, need a more center here. If null is true, the mean is 94 minutes. What we actually saw was 99 minutes. Right? And we wanted to see like if it was higher than. So this is the area I want, right? I'm looking for an upper tail. So we want the probability that z is higher than 2.5. So 2.5 here. I want this yellow area. That's what I'm getting at. So I'm going to go ahead and let's say 1 minus the probability that z is less than. So if I want to use the table, 2.5 can be split up into 2.5 and 0.00. So the 2.5 tells me which row to use, 2.5. 00 tells me which column. And it lines up here. So I have 0.9938. Now I'm going to want 1 minus 0.9938 over here. So I'm going to get 1 minus 0.9938. It's going to be 0.0062. And this is my one-sided p-value. And since I'm doing a one-sided test, this is good. This is what I want. So looking here, that's a pretty small p-value. In general, anything that's smaller than 0.01 is considered pretty small most of the time. So right here, 0.002 at the 0.05 significance level. For me, that's almost always what I fill in first. So one way to think about it, if I have 0.002 0.0062 is my p-value, and my significance level is 0.05, I would say it's fair to say, yeah, no, 0.0062 is smaller. So what this translates to is if the train company were really right and the average is 94 minutes as claimed, the probability that if I took a random sample of 25 or more of getting 99 minutes or longer, if what they said is true, only happens about 0.62% of the time, so less than 1% of the time. And I don't know about y'all, that's enough for me to go, maybe the null isn't true. So we're going to reject, because that's a small p-value. Small p-values, we reject the null. So then you can look back at that spectrum there, that green, yellow, red one. This is very strong evidence. So we have very strong evidence that, and now we have to put the alternative in context. It's not going to fit just in this blank spot, but the mean trip time, and then my population. So for all trips between Florence and Rome, and then I have to say, okay, well, what did the alternative say? Oh, it's higher than. So we have very strong evidence to suggest the average trip time for all trips between Florence and Rome, I'm going to add train in here, should be train, is longer than 94 minutes. So it's longer than what's advertised. But it is important to actually put the number there, the 94 minutes. So we have really strong evidence to support that this customer is probably right. It looks like on average these trips are between Florence and Rome are taking longer than the 94 minutes they advertise. So just a couple of notes, like why can't we accept the null hypothesis? The most easy analogy to use here, it's that idea of the court case. So suppose, like you're supposed to by default assume presumed innocent until proven guilty. So we're going to start with the null hypothesis is the defendant's not guilty, and the alternative is that they are guilty. What that means is if you get enough evidence, you'll reject the null, and so you'll reject the phrase that they're not guilty, and you'll conclude that they are guilty. But if you don't have enough evidence, you're just going to say, you know what, I don't have evidence, that they're guilty. Really, really careful though. So suppose you fail to reject the null. So the defendant's found not guilty. It's not the same as proving they're innocent, right? So if they're found not guilty, there are two scenarios. The first is that they are innocent, but then the second is you just didn't have enough evidence to convict them. So because we have no way of knowing which is which, you don't want to say you accept the null. We don't know that the null is true. We weren't trying to prove it was true or not. We were just trying to prove that the alternative was more likely. And if you aren't able to do that, then you pretty much have to say, oh, we don't have enough evidence to say the alternative is true. So be careful. If you say that the null is true or that you accept the null, we will jump on that super fast. That is like a button word for us. We will get that every time. So just know that is out there. Then I like to throw this out. I know it's an older meme. Change my mind guy. So they believe the null is true. So you try to convince them otherwise. So you have all of this, whatever evidence to convince them otherwise. If you don't change their mind, that's not saying that they're correct. It could mean that you just didn't have enough evidence to change their mind. So all of us have had that uncle that you argue with at the holidays, right? Just because you don't change their mind doesn't mean they're correct. It could be that they're correct, but it could also mean you just didn't have enough evidence to change their mind. So some notes on the p-values. So we like to talk about the strength of evidence that's supporting the alternative hypothesis. So the smaller the p-value, the stronger the evidence. I know it's a little weird, but one way to think about it is if the null really is true, a smaller p-value means what you saw in the sample is really, really weird. And so we don't think our sample's weird, so we think that maybe the null isn't true. The larger the p-value, the weaker your evidence is. And then there's this phrase, watch out. We kind of treat it almost like swearing nowadays. Statistically significant. If you hear the word statistically significant, what that means is the p-value was less than their significance level, and they rejected the null and concluded the alternative was true. So if you see that phrase, that's what that means. Just know that we're kind of creeping away from that. In part, there are some issues, and we'll talk about it, I think, in the next lesson just a little bit. So a four-part conclusion, although we're probably going to stick to doing two separate two-parts. So this is the two parts for the hypothesis test, right? So if I want to write my conclusion for a hypothesis test, I will have a statement that says whether or not I reject the null, I'm going to mention my p-value, and I'm going to mention the significance level. And then I'm going to say, okay, well, there is blank evidence that the alternative hypothesis is true. So that is my two-part hypothesis test conclusion. And then this is my two-part confidence interval conclusion. So you could say, okay, well, with blank % confidence, the mean train trip time is estimated to be between blank and blank, sort of thing. And then usually these are one sentence, but make sure that you include the point estimate. So mention what the mean was in the sample. It should be in there somewhere. So the point estimate for the parameter, that's just your sample mean. So for our train example, and granted, we did not sit through and calculate the confidence interval, and that's fine, but I'm just going to show you all four parts all written out. So we reject the null hypothesis with a p-value of 0.0062 at the 0.05 significance level. I know it's weird. You can say I reject. For some reason in stats, we like to talk in the collective we. I don't know, it makes us feel more valid or something. We do it a lot, obviously. I'm doing it right now. So you can say I reject, and that's totally valid. Just know that for some reason in stats, we tend to use we a lot. And then there's very strong evidence that the mean trip time for all train trips between Florence and Rome is longer than the advertised 94 minutes. So this is my two-part hypothesis test conclusion. Now for the confidence interval. So with 95% confidence, the mean trip time for all train trips between these two cities is estimated to be between 95.08 and 102.92 minutes with a point estimate, so this is just X bar, of 99 minutes. So something to note here, if you have 95.08 minutes and 102.92 minutes, looking there is 94 in there, right? I don't see 94. 94 is lower than that entire interval. This entire interval is above 94. So that's some solid evidence there, just there, that no, it's probably not going to be 94 minutes because 94 is not in that interval. So that's that example. Lesson 27, we're going to talk about a couple things to be cautious about in errors. And we have another full example as well.